been assigned. You have a quiz on Saturday, 8:30 a.m., 8:30 to 9. So if you want to put those 30 minutes to good use, you should arrive and occupy your seat by, let us say, 8:25 a.m. in the correct room number as appropriate for your section. Regarding makeup, we will discuss on Monday after the quiz. So it's fairly characteristic of our institute that when we cover the most important topic, that also happens to be the period of greatest disturbance. Okay. So that's who we are. So it's for us to maintain focus and have our own outlook to life. What else can I say? So why did I say this is the most important part of at least this course? Because we are looking at the local form of the mass and momentum equations that form the basis of our formulation. So almost all natural systems to engineering systems rely on this local form of the mass and momentum equations. So a farmer in Amravati wants to know why it does not rain. The answer lies in the flow patterns, not only in air but also in water, in the oceans. So combined, look at the scale of the problem. The clouds, the vapors get transported over thousands of kilometers and precipitate on an appointed day. And we want to predict, and we can, if we understand. Okay. So the starting point, if you talk of devices, whether it is a turbine or an engine or the flight of an aircraft, so the defense people talk of flight of missiles. The greatest variability or uncertainty in the flight of a missile comes from aerodynamic forces. And those forces are to be determined on the basis of the local form of the mass and momentum equations. System analysis is all right to give you the initial idea, but that overall idea is never enough. You have to go much deeper if you are talking of precision, accuracy, apart from overall. Saying, oh, overall I am okay, it's never enough. You need definiteness as much as possible. So that's how this part of the course becomes very important. So despite the importance, I have to confess that I have skipped not the foundations of the formulation, but the mathematical steps. I have referred you to a book like Kreyszig. But I will touch upon a few important points as we go along. So, we have seen that it matters whether you write del dot u or del u. So, there is a big difference between the two. I hope you have checked up the difference. This is the mass balance equation and the momentum equation. We had mass times acceleration, mass times acceleration is equal to body forces plus surface forces, all on a unit volume basis. Because we had that control volume formulation, we just dropped the integrals, which means on a unit volume basis. So, these are all terms like force per unit volume. Force would be Newton per meter cube. So, the next step is to provide something called material function, that is the mechanistic behavior of the material. In the control volume approach, we provide device level description. Here we provide material level description, because at the point you do not know what device you are talking about. So, the inspiration for it comes again from the Newton's parallel plate experiment, where we started by saying force is proportional to velocity divided by the gap between the surfaces. Proportionality constant is viscosity, and specializing it to a point, we have a linear relationship between stress and strain rate, which is sort of similar to proportionality relationship between stress and strain for an elastic solid. That stress and strain, here it is stress and strain rate. So, while plenty of solids are elastic within limits, you also have non-elastic, you may call them plastic, viscoelastic, viscoplastic, a whole lot of variations are possible. Similarly, it is not necessary that a fluid should display stress strain rate linearity, but the fluids I have been referring to, such as air, water, oils, they all show this linearity with a well defined viscosity. So, the moment you are given viscosity, it means you are treating the fluid as Newtonian. So, you can see there is Newton, the stamp of Newton everywhere. It is Newton's laws of motion followed by Newtonian fluid approximation. So, sigma is this matrix sigma ij, 3 by 3 matrix in 3D, 2 by 2. For our board work, we will use 2 by 2. And the response is the strain rate epsilon dot which is so strain in solid mechanics, or for an object, strain would be it's like a change in length over initial length, or it could be defined in terms of the angular deformation. So, it gets expressed in terms of displacements. When you talk of strain rate, you have the time derivative of displacement, which is velocity. You can almost see the way we are headed. If we relate sigma and epsilon dot in terms of velocity, we substitute into the momentum equation, and that becomes an equation for velocity. Okay, so, for a Newtonian fluid, talking about a linear relationship between sigma and epsilon dot. So, mass balance is a scalar equation, momentum equation is a vector equation, because forces are vectors, momentum is a vector. The relationship sigma is a, to use Kreyszig's language, it is a second order tensor, so is epsilon dot. We are talking about a linear relationship between two second order tensors. For our discussion, we may even think of those tensors as square matrices, 3 by 3 in 3 dimensions, 2 by 2 in 2 dimensions. Yeah. So, if you are worried about the implementation of the operators, please wait. I will have a brief comment on them. So, so your question is this del is a vector, sigma is a 2 by 2 matrix. How do you multiply the two of them? It is all matrix multiplication. Okay. You can multiply 2 by 2 matrix with another 2 by 2 matrix. You can multiply 2 by 2 matrix with a vector also. Right, 2 by 2 times 2 by 1 will give you 2 by 1, correct. Similarly, 1 by 2 times 2 by 2 will give you 1 by 2. You just have to follow the matrix rules.
My question was the differentiation correspond to second index or the first index?
Okay, we have not discussed index notation per se, but you just follow the matrix rules. Okay. So, del is to be treated as a vector. It is not just one derivative or the other, it is the combination of it. So, if you think of del as it is not I equal to 1 or 2, it is both I equal to 1 and 2. Okay, so, one can get lost in these little calculations, but the moment you have your grasp of the subject. What is the subject? I am talking about vector calculus, mathematics, matrix algebra. This is all like first year, maybe third semester, I do not know, either second semester or third semester mathematics. So, this index notation was popularized by Einstein, called Einstein's index notation, which may look formidable, but really is very simple. But if you do not follow the index notation, you can still apply the rules of matrix multiplication. So, if sigma and epsilon dot have to have a linearity, then the most general linear relationship between them will be of the form, let us say between x and y linear relationship, you write y equal to m x plus c is the most general form, m being the slope, c is a constant which is the value of y when x is 0. So, here it will be, I just write it as a epsilon dot plus b. Okay. So, you may want to add these indices I and I j. So, what is b? B is the value of sigma when epsilon dot is 0. So, this is for epsilon dot I for this equal to 0, it is a stagnant fluid. So, sigma I j is equal to minus p delta I j, and therefore, this expression is equal to b. So, you already have sigma I j equal to minus p delta I j plus a epsilon dot I j. The next question is what is a? You want this expression to reduce to the Newton's parallel plate experiment. You can think of that. A and b can be determined. How do you find a y equal to m x plus c? How do you find m and c? Find out y when x is 0, that gives you c, and then substitute x equal to x 1, y equal to y 1, that will give you m. Okay. So, we are doing something similar. So, by referring to Newton's parallel plate experiment, you will have, what did we have? We had sigma y x equal to mu epsilon dot y x. That tells you that a will be equal to, see, there is a factor of half, this half. So, this a then becomes, by reference to the parallel plate experiment, a is equal to 2 mu. It is factor 2 because epsilon dot has a factor half. We brought in that half as the average of delta 1 and delta 2, the angular rotations of the element that was under consideration. Okay. So, we have sigma I j equal to minus p delta I j. What is this delta? This is Kronecker delta, which is equal to 1 if I is equal to j, equal to 0 if I not equal to j. Okay. So, this now becomes our material function, which is in the language of fluid mechanics, it is called a constitutive relationship, also called a material model. So, you will clearly see the distinction between a natural law such as mass balance, momentum. These have enormous applicability, but the material model is for a class of materials like air, water, oil, where you have a linear relationship between stress and strain. A familiar example where it fails is blood, human blood, or if you have ink, you may not have seen ink. You only see this ink mixed with gel in your pen. But even 10 years ago, we used to have that fountain pen. I don't know if any, who uses a fountain pen in this room? Nobody. You have a fountain pen? You can't. That's a normal pen. That there was a bottle of ink and you had to fill that, there was a chamber and you had to fill it with ink. That ink is non-Newtonian. Why do you have to worry about that ink? Well, first of all, it is flowing through your, there was something called a nib, it would come out. How rapidly would it come out? It would depend on the hole in the nib. So, to do those calculations, you had to know the behavior of that liquid, which in the language of fluid mechanics is called a suspension, because it has particles. So is blood, which has suspensions. But blood is has RBCs and other types of particulates in an underlying fluid called plasma, which is very close to being Newtonian. It's a homogeneous fluid, which is close to Newtonian. These particulates make the fluid non-Newtonian. Non-Newtonian, what is that? It will not be linear. It will be now one way of addressing non-linearity is to make a function. What a? This constant a function of epsilon dot. That is a non-linear relationship. Independent of epsilon dot, then constant, you have a Newtonian model. So, when you now substitute, now let us this del dot sigma see, I am not able to draw this dot. If I put a dot at the center, it appears at somewhere else. I do not have control on that dot. But the dot, if you read books, make sure that, that you notice dot should be at the center. If it is 2.3, that is a decimal point, that is at the base. But if you are going to multiply 2 and 3, that dot will be at the center. Okay. So, in your answer sheets, make sure you show the dot. Let us see if I am able to do it right at least once. Now, I am trying to place a dot at the center. Yeah, that is how you have to write. Huh? If you do not put a dot, then all your matrix operations will go haywire. Huh? So, it's a critical symbol. So, what was sigma? It's, now, I am immediately going to transfer you to Kreyszig's mathematics. And how much is epsilon dot? It was half of that del u and all that. So, epsilon dot was half of see, I think in this book they do it in Cartesian coordinates. So, it may take you some 5 pages to work out the details. If you do it in index form, the whole thing becomes just one liner, just by looking at it, if you know the index notation. That I think Kreyszig's book does have a discussion of the index notation. And this whole thing works out to be so, I wanted you to distinguish between, let us say del u, here I have written del u, you can see that pencil symbol del u, which is not del dot u. Del dot u is 0 as per our mass balance equation, but that is del u. What is del u? I will comment on it in just a couple of minutes. Okay, so, now we have brought in the behavior of the fluid as Newtonian, which is a linear stress. What is a Newtonian fluid? If this is your question, definitely it was a question in one of the final exams of this course a few years ago. What is a Newtonian fluid? Newtonian fluid is one for which you have a linear stress strain rate relationship. Okay. What is an incompressible fluid? Incompressible fluid is one for which density is constant irrespective of the pressure distribution. but both density may change with temperature, viscosity also changes with temperature. You know that viscosity of oil, for example, will keep decreasing as you increase temperature. Okay. Viscosity of air increases as temperature increases. So, temperature is like an independent variable from outside. So, we are in the domain of stress and strain rate. Okay. So, velocity and pressure, these are the impacting variables. And then we ask, is viscosity dependent on these quantities? No, viscosity does not depend on velocity, viscosity does not depend on strain rate in the Newtonian fluid framework. Now, for gases like air, people have shown that if you change pressure by hundreds of atmosphere, okay, that means 1 bar is about 1 atmosphere. So, suppose I change pressure from 1 bar, which is atmospheric pressure, to 500 bars. Some slight change in viscosity does take place. So, it is a function of pressure also, but over a very large range of, but with temperature there is an immediate effect. So, which is why in this differentiation our field is also taken to be isothermal, so that I can keep mu as a constant during differentiation. Now, substitute del dot sigma in the momentum equation. So, let us write down mass and momentum. Which is okay. So, in this form there is no sigma, you have familiar variables like velocity and pressure. So, we have expressed mass and momentum in terms of velocity and pressure. So, the unknowns in these two equations are velocity and pressure. The momentum equation has 3 components in 3D. So, there are really 3 equations over there and 1 for mass. So, you have 4 equations. This is a system of 4 equations and there are 4 unknowns, 3 of u and 1 of p. So, that way the number of equations and number of unknowns, they balance. So, I was telling you whether it is a turbine or an engine or the Earth's atmosphere, whether it is the oceans or the lakes or the breeze going over it, transporting water vapor, leading to cloud formation, to precipitation. So, you have the same system of equations derived by independently by Navier and Stokes. It is called Navier-Stokes equations. So, in this course we will use Navier-Stokes equations to arrive at solutions. See, saying flow will follow these 2 equations is not useful, because what do you want? You really want the distribution of velocity, distribution of pressure. You want u, you want p. So, you have to solve these equations. So, we will discuss solution of these equations as we go along. Okay, let me jump to, let's look at the body force term. Yeah, the second part simplifies to mu del square u. How exactly you have to work out? I am not saying it is self-evident. Those are calculations that stem from maybe index notation if you follow his discussion, or you may have to work it out. You will have to express del u. So, I will come to, I am not going to show you the derivation of this form from that form, that I am going to leave to you, but I am going to comment on what is del u in structural form. Okay. The fact that what is that superscript T? Transpose. If I am going to say transpose, it means it is a matrix form. Okay. So, let us look at body forces. An example of a body force was the gravity field, which we write as minus rho g k. K is a unit vector in the z direction, which is vertically upwards. So, if I define, let us say I define a modified pressure as P plus rho g z, then please show that this Greek symbol I forgot to bring, what was it, a chi, chi minus, I hope you got that table of Greek symbols. Chi minus gradient of P is minus gradient of P tilde. Okay. So, these two terms I do not have to show chi and gradient of P separately. I will just write gradient of P with the understanding that it includes the gravitational contribution. Okay. So, you can, this is a simplifying step. So, I do not have to show this chi every time. So, when you solve for P, then you interpret it as P plus rho g z. So, if you get P, then that is when you get P without chi, that means you got P tilde. Okay. And then you can get P out of it by subtracting rho g z. Okay. But like flow, suppose I have flow in a horizontal tube. Okay. The extent of the fluid material in the vertical direction is very small. So, you may even drop. Let us say you are working with air. In air, density of air is very small. So, much of the time, unless you are talking about kilometers of an air column, otherwise over 10 mm or 50 mm, there is hardly any impact of the second term. Okay. If the tube is vertical, yes, gravity is very important. So, this entire thing can be written as, so you already have this simplification. Okay. So, body forces can be absorbed in pressure. So, in the subsequent discussions, unless I have to, I will not show. If I do not show this chi, it means it is contained in P. Okay, so that was one comment. The second is so let us work in Cartesian coordinates. where the x and y components of velocity are u and v. So, del dot u you know how to evaluate. You can try your index notation if you wish. You can show components. How do you you have to multiply them? Suppose you use matrix notation. This will be written as a 1 by 2 vector, and this is 2 by 1 vector, right. So, this is 1 row 2 columns multiplied by 2 rows 1 column, giving rise to u x plus v y, okay, scalar. So, it gives you a, this is 1 by 2, 2 by 1, that gives you 1 by 1, the scalar quantity. If you want to do del u, you have to reverse it. So, it is, this is 1 by 2 by 1, and 1 by 2, which will give you a 2 by 2 matrix. So, sometimes this dot, when you show a dot, it is called an inner product, and this second form del u without a dot. So, let me write no dot. It is called outer product. And the transpose will be transpose of this matrix. So, one other comment, just wanted to comment on this strain rate. Was not sure if you absorbed the details of how a strain rate tensor is constructed. It is constructed in analogy to the stress tensor. Why should it be analogous? Why should strain rate have analogy to the stress? Because we are trying to set up a linear relationship between them. Okay. If something varies linearly with another, the two have to be similar, they have to be correlated, right. So, strain rate is similar to stress tensor by construction. So, sigma I j so, this is how we indicate our stress tensor. It has components sigma x x, sigma x y. So, if sigma has to be analogous to epsilon dot or the other way around, then epsilon x x has to be similar to sigma x x, epsilon y y has to be similar to sigma y y. So, component wise they have to have a linear relationship, So, what is sigma xx doing to this element? It will result in elongational strain of this element. It is pulling this element. So, if you think of an incompressible element, so this dashed line is the initial shape of this element, and then after you have pulled it, it has become longer. Okay. So, this elongation is what we had defined as epsilon dot x x, which was the time derivative of this extra increment that is elongation per that divided by the initial length. Okay, this ratio you understand is the strain, psi is the displacement of the reference point A prime. So, the extension of this element in the x direction correlates with sigma x x. And this is equal to u x. Okay. This u suffix x is derivative of u with respect to x, partial derivative. So, similarly, we had component wise we had set up then for shear strain. This was the initial element, which after some time deformed through angles delta 1 and delta 2. If you choose to work with the average of delta 1 and delta 2, well, there is a hidden message here, but the way I have written it is no longer hidden. It shows the strain rate tensor to be symmetric. Okay. So, by construction, so delta 1 plus delta 2 is also equal to delta 2 plus delta 1, which makes it a symmetric tensor, and epsilon dot x y has to have correlation with sigma. So, the question to be asked is sigma symmetric? Not necessarily, but it turns out it is symmetric, and sigma is symmetric for it just this is it's an observation. Okay. So, you can develop Navier-Stokes equations where sigma is not symmetric, but it turns out that for the fluids I just referred to, air, water, oils, fluids that overall demonstrate Newtonian behavior will have a symmetric stress tensor. Now, what will happen if it is not symmetric? This is at a point. So, sigma x y and this is sigma y x. If these two were not to be equal, then at the microscopic element level, there will be an unbalanced moment that will have to be cancelled by the molecular structure of the material. these two were not to be equal. So, but air, water, these have their molecular structure is very, very simple, elementary, small. These are not long chain molecules like polymers. Some polymers which have a very, 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 very long chain, molecular chain of atoms may be twisted microscopically, and sigma xy may not be equal to sigma yx, but for simple materials of the type we have in mind, there is no microscopic moment at this level, at the scale of this element, which makes sigma symmetric, and which is why we have made epsilon dot x y equal to epsilon dot y x as the average of delta 1 and delta 2. Okay, so, that is now, so, let us look at this property. This is sigma x x, sigma y y, sigma x y, and then you had the strain rate tensor, so these terms correlate term by term, sigma x x with u x, sigma x y with the strain rate, and even further, you know the trace of the matrix sigma. What is the trace of the matrix sigma? The sum of all the diagonal terms. So, this minus 1/3 trace sigma, how much will it be? Minus 1/3 trace sigma. Sigma trace sigma is sigma x x plus sigma y y, maybe sigma z z. How much was sigma I? We wrote that expression. What are the diagonal terms of sigma? Pressure. Remember that? So, let us start on a fresh page. To mu epsilon dot x x, that was u x. This is to get the trace, you have to add these two. This is equal to. So, here it is turning out to be, let me put sigma z z also. So, that you have minus 3 p plus 2 mu, what is u x plus v y plus w z? It is del dot u. Which is 0 for an incompressible fluid. So, minus 1/3 trace sigma is p. And what is the trace of epsilon dot? Epsilon dot had u x v y on the diagonal elements. So, this is w z in 3D and only these two in 2D, which is del dot u, which is also equal to 0. So, we are talking about correlation between sigma and epsilon. Why correlation? Because it is a linear relationship. So, there is a linear relationship between sigma xx and ux, sigma xy and the strain rate. Taking it a step forward, the trace of sigma is pressure and the trace of epsilon dot is del dot u. What is del dot u in physical terms? So, it was the mass balance equation. What is mass balance equation? It is inflow minus outflow, is it not? So, it tells you, so this is and that is turning out to be 0. So, what happened to the correlation between pressure and the difference between inflow and outflow? What does it mean? The del dot pressure should have a linear relationship with del dot u, but del dot u is 0 for the incompressible fluid. So, what happened to the cause effect relationship between pressure and the difference in the volumetric flow rates? Any comment? Only comment is your finger going up. Yeah? Oh, it's not going up today? So, well, it's an interesting thought. So, we'll deal with it on Wednesday.